So we noted how this mechanism only works for Cl2 and Br2, but there is going to be a difference using whether you use Cl2 versus Br2 will depend on what halogenated product you want, not just whether you want a chlorine or a bromine on there, but where you want it to go. So let's look at the differences between chlorination and bromination via these radical mechanisms. So we're going to start with propane, CH3, CH2, CH3. Note if we're looking at monochlorinated products, because we're going to put chlorine in, there are two possibilities. We could put the chlorine at the end, or we could put the chlorine in the middle. Now, statistically speaking, if you add the chlorine radical, we know the first step is we're going to make Cl2 chlorine radicals. It can come in and it could hit one of these end hydrogens, or it could hit one of the hydrogens in the middle. Note, there are 6 hydrogens, 3 here and 3 here, that are equivalent, and 2 here. So you'd expect that if the reaction was purely statistical, we would get a 6-to-2 ratio. A 6-to-2 ratio, well, 6-to-2 is 3-to-1. We'd expect 3 times as much of this chlorine at the end versus the chlorine in the middle, simply because there's 3 times the number of end hydrogens as there are middle hydrogens. But that's not what we actually see. When we run the reaction, we find we actually get a 1-to-1 mixture of these two. Why is this? Why do we get a 1-to-1 mixture? Because, as we learned earlier, secondary radicals, which this will come from a secondary radical, are more stable than primary radicals. Recall, in the mechanism, initiation, you make chlorine radicals. Propagation, a chlorine radical abstracts a hydrogen to give an alkyl radical. A primary alkyl radical, if the chlorine abstracts one of these, is less stable than a secondary alkyl radical if the chlorine radical abstracts one of these hydrogens. So we will get more of the secondary radical because it is more stable than the primary radical. We still see some, but statistically we're expecting 3 times as much primary as secondary. In reality, we get the same amount of primary and secondary. To put it in numbers, 3-to-1 would be 75% to 25%, where this is 50-50. Okay, because of the stability of that secondary radical. All right. It turns out, however, that chlorination is much faster than bromination. And that's why it gives this mixture of products. So we say chlorination is pretty much unselective. Recall when we were looking at why iodine and fluorine don't work, iodine is too slow, fluorine is just too violent and too fast. So bromine is next to iodine, so we'd expect the bromination reaction to be slower than the chlorination reaction, and it is. And because bromination is slower than the chlorination reaction, the reaction has time to get the more stable product. The longer a reaction takes, the more likely you're going to end up with the more stable product. And since bromination is so much slower, if we do the same reaction here but with bromine and add heat or light to our propane, we find that we get 99% of the more substituted product, only 1%. Because this substituted, the secondary alkyl halide comes from a secondary radical, which is more stable than the primary radical. Because this reaction happens more slowly, you have time for the secondary radical to develop. So what would iodine is too slow, or reacting with I2 is too slow, you won't get anything. There are some books that would say if you used fluorine, F2, you would get the purely statistical 3-to-1 ratio because it happens so fast. I think the truth is you get that 3-to-1 ratio of those two maybe, but you'd also get difluorinated and trifluorinated products. It's just 2 reactors going to give you a whole mix of everything. Plus it's all awful dangerous. All right, so let's look at this molecule right here, the cyclopentane, 2 methyls here, ethyl off here, and let's number the carbons that have hydrogens. Very important here. You can only put a halogen, a chlorine or a bromine, on a carbon that has a hydrogen on it, because the first step in the mechanism after initiation, the first propagation step, is hydrogen abstraction. So note this carbon right here, this quaternary carbon, has no hydrogens on it. You cannot put a halogen on this carbon. It's already got 4 carbon-carbon bonds. No halogen can go on there. So we could put a halogen on this carbon here, or this carbon here, 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 here. And I've noted with these numbers the number of hydrogens. There's 3 hydrogens on this carbon, 2 on this carbon, only 1 hydrogen on this carbon, 2, 2, 2, 6, because this methyl and this methyl are the same. So if you added chlorine 2, what's going to be the ratio of products? Well, we could put a monochlorinated products. It could be here, or here, or here, or here. What's the ratio? Well, it's 6 to 2 to 2 to 2 to 1 to 2 to 3. Just like above, it was 6 to 2, because up here there were 6 of these, and see, hydrogens, and 2 in the middle. Down here it's 6 to 2 to 2 to 2 to 1 to 2 to 3. That's the statistical possibility. And note, because we have this 1 here, we can't reduce it to 3 to 1 to 1 to 0.5. No, that doesn't work. So it is a 6 to 2 to 2 to 2 to 1 to 2 to 3. That's the statistical probability. What do you expect to see, however? Well, we note that carbon 1, if there's a halogen that comes off of carbon 1, it would come from a tertiary radical intermediate. So we'd expect to see more of the product with the halogen with the chlorine on this carbon, because it comes from a more stable radical. But this is chlorination that happens fast, so we'd expect to see more of this, but we'd still expect to see all possible products here. More of this than statistically expected. Note these, if you put the halogen on this carbon or the halogen on one of these methyl groups, we'd expect that to come, well, that would come from a primary radical, which is less stable. So we'd expect to see less of the product that has the halogen here or the halogen here. And unfortunately, that's about all we can say. We don't expect a 6 to 2 to 2 to 2 to 1 to 2 to 3 ratio. We'd expect less than 6 here and more than 1 there, and less than 3 there due to stability. Either way, 1, 2, 3, 4, 5, 6, 7. You're going to have a mixture of 7 products that you then have to separate from each other, and all of them are monochlorinated hydrocarbons. That's going to be a mess. That's probably not synthetically useful. But what if instead of Cl2 we used Br2? Well, we know bromine is a slower reaction. Bromine is going to only really form the product from the most stable radical. The most stable radical would be the radical that came when you put the bromine on here, a tertiary radical, so you'd only make this 1 compound. So what we tend to find is bromination tends to be more synthetically useful than chlorination, because we only make usually 1 product, the most stable product. The problem is, what if that's not the product that you wanted? What if you wanted the halogen right here? Well, then you've got a mess. The best thing would be to find a different way. Truthfully, the best thing would find a different way than going through this molecule if you wanted. This is a starting material if you wanted to put the halogen right here, because you'd have to put a chlorine and you'd have to fish it out of this mess. If you absolutely cannot find another way to do it, then you'd have to do this, and you're going to spend a long time on your separation schemes trying to figure out how to get that 1 product. All right. So let's use this knowledge of halogenation for synthesis. Say you had cyclohexane and you wanted to make this cis dihydroxycyclohexane. How would you do that? Well, to me, I would look at this and say, wait a minute. This two hydroxy groups on a cyclohexane next to each other, both in this coming out in the same direction, that is syn dihydroxylation. And what reagent did we learn from the last chapter that does syn dihydroxylation? That's right, potassium permanganate. So I would start with a little retrosynthetic analysis. I would start saying, okay, I know I can make this if I had cyclohexene and potassium permanganate. So I would start, okay, here's my product. I know potassium permanganate and cyclohexene will make that. So now my question is, how do I go from hexane to hexene? Well, the other thing I know is if I've got a hydrocarbon like hexane, the only reactions they do are these halogenation reactions. So what if I put a chlorine on here? Just Cl2H put a chlorine on here. Now, after our last discussion, you might be saying, well, why don't you use bromine here instead of chlorine? Two reasons. Reason one, you would get the same product. Since all of these are CH2s, the chlorine will only go on one of these CH2s, assuming you kept chlorine as a limiting reagent. You'd put the chlorine on there, so it doesn't matter chlorine versus bromine. The other thing is, while bromine is nice and it gives you the product from the most substituted radical, Br2, bromine liquid, is really toxic stuff. It is nasty. Br2 liquid, the vapor, and bromine gives off lots of orange vapor. That vapor is about 40 to 50 times more toxic than hydrogen cyanide gas. So Br2 is a pretty dangerous reagent to use. So if you can avoid it, do it. Chlorine is cheaper and it's less dangerous. Now, it's still pretty nasty. You breathe in this stuff, you'll die. But it's less nasty, or it's not as nasty as bromine is. So use Cl2 and run our reaction. We'll put a chlorine here. So then the next question is, if I've got an alkyl halide here, how do I form an alkene? Oh, that's right. E2 elimination with a sterically hindered base, such as potassium tert butoxide. That would be the way to do it. Put in some tert butoxide in here and get this elimination. You could probably use sodium hydroxide and heat it up because heat favors elimination. We remember that. The problem is this is a secondary alkyl halide with sodium hydroxide. Recall from earlier exams that a secondary alkyl halide with hydroxide means you could get the SN2 and the E2 products possible. You heat it up and you favor the E2 product. But heck, let's put in potassium tert butoxide so we only get E2 instead of hydroxide, where we'd have to worry about the SN2 product. Only elimination. So that's the deal. That's how I'd work this reaction. I'd start with retrosynthetic analysis because I know how to form this dihydroxylated compound. Syn dihydroxylation is this step. Then I'd say, well, I know I need to put a halogen on here. The only thing it can do is radical halogenation. And then I just had to figure out how to go from here to here, which is an obvious elimination. Cool. And then everyone has the same question. Well, what about stereochemistry? Well, the thing to remember, what is the hybridization of a radical carbon? That's right, it is sp2 hybridized. Its shape is trigonal planar, which means when you formed that radical, that carbon radical that's trigonal planar, and then the chlorine or the bromine, that halogen came in, on which side did the halogen come in on? That's right, a 50-50 mixture of each side. So if your carbon, your radical carbon, becomes a carbon with 4 different groups on it, you've got a chiral carbon at that point, and you're going to get a racemic mixture. Note, here we go. We've got butane here, achiral. We add Cl2. Note, if we're monochlorination by keeping Cl2 as a limiting reagent, we're going to get chlorine on the end, or chlorine right here. If you put chlorine on the end, that's achiral, but if you put the chlorine here, well, now this carbon has a methyl, an ethyl, a hydrogen, and a chlorine. That's now a chiral carbon. You'll get a racemic mixture of the 2 enantiomers of that carbon. All right. So let's look at this right here, and we're going to really specify this reaction. If we're going to put Cl2 in with this molecule, note we started with a chiral carbon already. Ooh, we're already optically active. That's nice. We started with a chiral carbon here. Let's only look at this hydrogen being abstracted or one of these hydrogens being abstracted. Let's ignore the methyls, because we know with the methyls that's going to give us a chiral product. So let's only pay attention to the chiral products here, taking one of these hydrogens, or this hydrogen here, or one of these hydrogens here. If we abstract this hydrogen and put a chlorine on there through our radical mechanism, note it's still a chiral carbon. We end up with those 2 enantiomers. Note if we take one of these hydrogens down here, this carbon is not chiral, but then this chlorine can go in from the top side or it can come in from the back side, because we generated this chiral carbon, which means we have a 50-50 chance of the chlorine coming in from one side, 50-50 chance coming from the other side. But note, when you did the reaction with this hydrogen, all of our reaction was occurring on this carbon. This is the carbon that became trigonoplanar. This carbon here, nothing happened to it. And so, since no reaction happened at this carbon, it is still the bromine coming out, the hydrogen going back, because no reaction occurred. So look at here, we now have 2 chiral carbons in this molecule, and this one stayed the same. So if you have 2 chiral carbons, but you only switch 2 groups on one of them, these 2 are diastereomers. Now you're thinking, wait a minute, diastereomers, don't we have to get enantiomers here to cancel out the optical rotation? No, we do not, because we started with a chiral molecule. Our reactants are optically active, therefore we can have optically active products. We can end with just the diastereomers. Cool. And last thing to mention right now, so some good news. Let's look at some good news. The ozone layer. All right. Okay, a while ago we invented molecules called chlorofluorocarbons, CFCs, and this is an example. It's a carbon with a fluorine and 3 chlorines, that's Freon 11. Here's 2 fluorines, 2 chlorines, that's Freon 12. We had molecules with 2 carbons with 3 chlorines and 3 fluorines, all sorts of these chlorofluorocarbons. And they are very nice because, one, they are unreactive. You breathe this in, you breathe it back out. They don't really react with anything, usually. And 2, they can go through compression and expansion cycles very nicely. And I don't know if you know how well air conditioners work, but air conditioners work by compressing a gas, which then the gas will heat up. You then have a fan blowing or something that gets rid of that heat, and then you expand the gas, and when it expands it cools down, and then you use that cooled gas or that cooled chamber to cool down your food in your refrigerator, cool down your house and your air conditioner. But it all has to do with compressing a gas, which will heat it up, get rid of that heat outside, and then expand that gas so it'll cool it down, and then using the cool air to cool other things down. Which means the gas in your refrigerators or your air conditioners get compressed and then expanded, and compressed and expanded, compressed, expanded over and over again. And it turns out lots of gases can't handle that. Nitrogen gas does not do well under those situations. Oxygen gas, forget about it. But these chlorofluorocarbons work really well. They can get compressed and expand quite a bit, and not only can they handle it, but they don't damage the hoses or the containers or anything else. And so that's good. But then we found there was a problem, because while these are fairly inert, they don't react down here in the normal atmosphere. Once they get up into the upper atmosphere, it turns out that they respond to ultraviolet light and generate radicals. So let's look at the situation. We have the ozone layer, and normally the ozone layer, we have ozone molecules, that's way up there. The sun is shining off quite a lot of ultraviolet light on us. So this H nu, this photon of light, is in the ultraviolet region. And we really don't want that ultraviolet light to hit us, because then we get skin cancers and cataracts and eye cancers and all sorts of bad things. We go blind, damages our retinas, damages us. Lots of bad things come when we shine a lot of ultraviolet light on ourselves. So the ozone layer, though, if you have two ozone molecules, they will interact with two photons of ultraviolet light to make three O2 molecules. And so as the ultraviolet light is hitting the Earth, ozone absorbs it to form three O2 molecules. And the thing is, this reaction is reversible. After a little bit, these three O2s will combine to form two ozones back again, so the ozones can keep doing their job. The trick is, when the three O2s react again to form ozone, they don't give off ultraviolet light, they give off heat. So our ozone layer is simply an engine that converts ultraviolet light into heat. Ultraviolet light photons get absorbed, and then forms O2. When that O2 reverses and forms O3, it gives off heat, which means these ultraviolet light photons do not hit the Earth. The problem is that when these chlorofluorocarbons get up into the ozone layer, the ultraviolet light hits them and forms these two radicals. And this chlorine radical can then react with an O3 molecule and form an O2 plus ClO dot. Then the ClO dot plus O3 goes to two O2s plus the Cl dot. Ooh, check this out. We end with the same radical we started with. So this is the initiation step. No radicals, we generate radicals. Then we have a chlorine dot that we start at this step, makes this reactive intermediate, which reacts with another ozone to generate our initial radical again. So what's this chlorine dot going to do? Oh, it's going to react with another ozone, which will convert it to an O2 and a ClO dot. That ClO dot will react with another ozone to make two O2s and a Cl dot, which will react with its propagation steps. All right. Note, if we were to do a good old Hess's law and add everything up, we would see, okay, the chlorine dot starts here and ends here. Yes, it's a catalyst. It's a radical catalyst. This intermediate is gone, so we end up with two O3s go to three O2s. It's this reaction up here. Well, so what's the big deal? So we've got two O3s going to three O2s. But note, in this process, one photon of light generated this radical, which kept regenerating itself through this propagation mechanism. It's estimated that one chlorine radical will go through the propagation process about 40,000 times before it meets another chlorine radical or an O2 radical somewhere where it can get taken out through a termination step. Which means this one photon of light made this radical killed 80,000 ozone molecules. So one photon of light took out 80,000 ozone molecules, where instead one photon of light normally takes out one ozone molecule. This isn't exactly accurate, but it's pretty close. What that means then is for every one chlorine radical that gets produced, since it kills 80,000 ozone molecules, 80,000 photons of ultraviolet light make it to Earth. That's not exactly the case, but it's not that far from it. So, this is bad. So then we started banning these types of molecules, these freons, in our air conditioners. We had to find other methods, other gases for air conditioning. Our aerosol cans, our Aquanet used to have freon in it, now it doesn't. And because we have banned these, at least the developing countries have banned these molecules, what we have found is there are far fewer chlorofluorocarbons getting to the ozone layer, and the ozone layer is healing itself, because as long as you don't have these radicals up there, the reverse reaction can occur and the ozone can regenerate. And that has been happening. It is estimated by 2050 that the ozone hole, the problem with the ozone layer, will get back to where it was before we started pumping all these chlorofluorocarbons up there. So that is some good news.